We could talk about what we've done so far in the semester as part of a review. I see that my status, I have really poor signal quality. Can you guys, anybody have a suggestion?
Are you on Wi-Fi or are you on like a LAN cable?
I'm on Wi-Fi up in my room over the garage because I don't have so yeah. I've really been struggling with the Xfinity people that I've been trying to upgrade, and they run me through the ragged, saying I run through the test, and the test always says that I have excellent speed.
I'm sure we can. It's like it's up and down, so I think we'll be fine. Oh, maybe not.
Now he's gone. So no exam. That's what I'm getting at here.
Spoke too soon. Does this mean he's gonna postpone the test?
I doubt
Probably
it.
not.
Yeah, I mean, you can't really postpone it any
Eli,
farther.
how hard is assignment 6?
Um, two, if I did it right, it's just long. You have to do a lot of iterations. It's exactly like one of the problems that we did in class.
Okay, like
For
the one where he like kept going and then went back in the book and
Yeah,
checked
where you
it.
only did like two iterations, but this one, if I'm doing it right, has like four. Um,
Okay.
then the third problem, I don't know if I did it right, but it wasn't too bad. You just have to, he uses it like an equation that is in one of the note examples that he didn't do in class um for the
Like one of the videos?
yeah.
Alright, perfect.
And then the first one I'm still doing, and it's just
The first
I
one's the only one I did.
I didn't. I've been just waiting on that one, and then like I don't know, it always messes me up with like which way the forces are supposed to be going on like when you draw
Oh yeah.
your shit.
Well,
Like
no, I hear you, but like since we're doing the input, it doesn't really matter. If we were doing like one of the idle gears where like we have two different axes, then it
but he
would
wants
matter.
an FBD of all the gear shafts, so I'm just doing them all. I don't know if that's what he wants or not.
Nah, you're tweaking. You're just supposed to do he just wants the bearing for the input and output.
I don't know. Oh well, I guess I'm
Just
doing
like
all of them. I don't
the
know.
one axis.
Yeah, yeah, and because it's the input and there's only one gear on that shaft, like it's only one axis. Like if it was another gear, like an idle
But
one,
then
like
in
with
bold, he says you must draw FBDs for each shaft to find the bearing loads.
exactly. So yeah.
So you would
Well,
have to do that all.
All right,
no,
looks
no,
like I'm
no.
not doing
Nah,
it.
I, well, bro, I got you. Read the first sentence. The second line says for input and output shafts.
Yeah, and then it says you must draw FBDs for each shaft after that.
Yo, what are you guys talking about?
I don't know, man. I don't know.
The
You're in big
homework
trouble.
or
Which
assignment
homework
6.
6?
Yeah.
So what
Yeah.
happened
Ben, you want to
is
do that tomorrow?
so
Yeah, I might start it tonight, honestly.
All right, let
We'll
me
see
know.
though. We'll see how it goes.
Eli, I think you're bugging, bro.
I mean, I might be bugging, but I'm still gonna do it. I don't know.
I mean, it's not gonna hurt you. It's just
I'm already on like I've already done like 4 out of the 5 shafts that I have or some
Jesus
shit, so I might as well
Christ.
just like
So
Doing
yeah,
the
continue.
project?
are you in Milanovic? He transferred Milanovic, right?
Yeah, what'd you get?
I got a 67.
Oh shit, me too.
Oh, really nice. I was honestly not that mad because I'm so happy she's giving us points back.
Oh, I knew she was. As soon as I saw like the first question, I was like, "Yep, there's no way anybody else is gonna know."
Dude, the average for your class was like, what was it, a 45 or something?
47. Chill, chill, chill. We up there
Yeah, that's crazy.
with the 51 median.
Oh, okay, I got you.
No, but
I
I have a
wasn't
I
sure
think
bunch
I
if
of
you
know the
did.
friends
two
that
people
never
that
had it,
caused
never
that to go
cleared.
down.
Yeah. Well, Jake did pretty much same as us. Yeah, I don't know.
She
I'm just
does it
happy to
every
get
year.
points back.
Every time I've had her as a teacher, the first one is always a fucking.
Oh yeah, this is my fourth time with her. I've never gotten above a 60, a 70 on her first exam.
Yeah, I'm not worried about it.
So what's up with the deal? Can he just not join?
I mean, he was
Uh,
joined. It sounded
he
fine, but then it's
joined
like
and then he
internet
got
went.
kicked like immediately. Yeah,
Oh, that sucks.
Now we just
I'm just
chilling.
playing video games, so.
I'm just doing the homework.
He's having like Wi-Fi problems or something.
But the directions always confuse the shit out of me. I hate that part. Like which way the gear and like which way to do the forces, because sometimes you do them with the fucking rotation of the gear, and then sometimes you just don't. I don't know.
You're
I
talking
think
about
when
like
it's the
FT and all that,
I
right?
just
Yeah.
Yeah. So I don't know. Did he have
when it's
that
the
one
gear that's
homework problem that we did? And there's also the homework, the example that's in the book. But I don't know. I feel like the key is like, so like when you're specifying it, you usually do like 2 to 3 or like 3 on 2 type shit. And then I don't know. It's based off of that somehow. If that helps.
isn't it the driving gear, like the gear that's like giving the power, the forces are against it, but the one that's being driven, the forces are with it.
Right. But when you apply that to the shaft, like which one is which, and then also
Yeah.
Eli, like if you're doing an idle shaft, you have like the gear from the shaft above it or the gear above it and from the gear below it. So like,
Yeah.
I don't know.
That's what I'm doing out here.
That
I'm
seems like a
working with how many
tomorrow's
pages
issue.
do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 8 pages, and I still got more gears to do, more shafts.
As long as
That's
you
only
know
the
you're
first
not
row.
supposed to do that, bro.
I mean, well, I'm already too deep. You know, I might as well just.
I feel you. I feel you. I don't know. I feel bad, man. That's. Did you do the practice exam?
The what?
The practice exam for you?
No, I haven't even looked at that.
I'm
I'm
looking
just
at it right now.
just trying to get all my work done like for the week, like today and tomorrow. Then I'm just gonna
Nice.
fucking grind, study for that shit.
Hopefully this test isn't too crazy.
That's
Hope
what I'm
it's
hoping.
With Deal's test, you just can't stop moving your pencil.
Yeah.
Do you think like the shit from 370 is gonna be on there or no?
Well,
He had it on the
did
practice
the review
exam,
have
and I'm
some?
really
Yeah,
mad about it. I'm like
yeah.
really
Some of the
upset.
practice stuff has stuff from 370, so I don't know.
Well, I asked him. He said he
Nah,
usually tries to, but he usually doesn't
What the
put
fuck is
370
that?
on there.
He tries to, but he doesn't.
Or yeah, he wants to, but then he gets to the exam and then he just doesn't put it in.
yeah, like the
He
first
has
one
like
on the
SN
exam.
diagrams and like minor and major and shit like that.
Yeah,
And
I'm
it's so
looking at like a handle problem. I see you know.
what the fuck is transverse shear? What the hell?
Remember that's the one
That's
that
the
like doesn't get applied much.
Nah,
It's
I'm
the
just playing. I'm just playing. I'm just playing.
Alright, I was all I'm seeing is like flashbacks from 370 looking at this thing for like half the problems. There's a fucking
Even
Morse
like
circle. Like, I remember
PTSD.
how to fucking do that shit. Yeah, no, get out of
Right.
here. Then an SN diagram. Yeah, no, I don't remember how to do that.
I still got my book marked up, so I'm just gonna bank on that.
I'm just
Yeah,
happy
that's
that
kind of what
the
I'm hoping
second
for.
exam will be take home. That's nice.
Yo, we can't have an equation sheet, right?
Nah, you just have the book.
Oh. Oh.
Oh, he's coming back.
All
I have
right.
sticky notes for all the examples. Ooh,
This is I'm a
Hello?
little frustrated. I'm here.
Hello.
Do you hear me?
yeah.
Yep.
Yeah, we can hear you.
Okay. All right. Got to go move to the kitchen and then restart my computer. That's what they would have made me do anyway, right? If you'll go to the help desk, turn your computer back off and on. Now I don't have a second monitor, so I can't look at my solutions while I try to answer questions, if I can answer questions. All right, so let's try to get some usefulness out of this. Open up my little visualizer thing. Oh yeah, I need to share screen. Share screen. I don't know what that little beep thing is. There it is again. Where's it coming from? I don't know. Is this thing still being recorded? Is it all? Is your conversations while I was away? That got recorded?
Yeah, but you probably should.
Probably.
All right. So let's see. I made a new folder here under exam prep. All right. So anybody got a problem type or a specific problem they'd like to start out with?
I got a question about like what exactly is going to be on the exam because I
Okay,
remember.
I like. Wait, I just want to quote what you said. I have a question on what exactly is going to be on the exam. I just
Yeah.
want to point out that that's what you.
Just because you mentioned a little bit in class, so I was wondering if you could expand on it. Like, I remember you
Okay.
said that you were gonna try to put some 370 stuff on there. And so, yeah.
Yeah, I usually attempt to put something on there, but mostly what we've covered has been chapter 13, 14, and 11. So I often find that's enough things that I would like to ask 4 problems, but most students don't end up finishing if I ask 4 problems. So a lot of times I have to ask 3 problems. It's just a kind of a I don't know, something I observe. So if I were to ask 4 problems, one of them would have some type of 370 content built into it. So if you take a look at like the review problems, I included there are actually some problems for, like problems like this right here. Of course, this is too long, but I wanted you to, have some practice in doing some maybe I could ask something like give me the principal stresses of something or some type of fatigue problem. But once again, that's not the whole point of the course. I just want to make sure that we have some of those skills. Even that first week of class was, the first assignment was supposed to be like a 370 partial review. So that's what I meant by that. But yeah, so like I haven't I haven't written the exam yet. I need to do that today. But if I could, when I time myself, if I could get it so that I ask 4 questions under 37.5 minutes, which is usually what my range is, to try to get a 1 to 2, 2 to 1, whatever, ratio of time for me taking it and working the problem slowly. That's usually how I kind of measure the thing out. But if I can't get it underneath 37.5 minutes with 4 problems, I'll have to do it with 3 problems. If it's 3 problems, I probably won't be asking anything related to ME470. So that's full disclosure. So I know I don't answer your exact question of what exactly is on there, but that's my plan. So in terms of the topics that we covered, aside from just being chapters 13, 14, and 11. You can see just like some of the homework problems are usually a pretty good guide. I also posted up under here problems that are suggested. This is what Dr. Ghosh would give out to his students and say, here, make sure you could do all those problems, and then that's what he would draw from for the exam. And I'm not that much different, just here are problems that, in addition to these practice problems that I put together, I would suggest that you should look through. And quite often that's usually, well, I think through a lot of the review sessions, this is what I end up doing, is just like going, picking out a problem and saying, oh, hey, let's look through this one. And, so I have all these. Wow, that's really fuzzy. You can't really, I need to get a better screen capture of that. Got an ugly one. I expanded it, made it larger, and now it's all fuzzy. But anyway, here's like problems that I'm suggesting, or these actual ones Dr. Ghosh suggested. I don't think I would ask this one, but it's not impossible to do. It's just we haven't done many like here. These actually helical gear. You can't arrange a helical gear at a 90-degree thing like that. So that probably confused students, but it can be done. Like this is a planetary gear. I'm going to want you to be able to do a planetary gear problem. I did notice that people struggled with the homework planetary gear problem. So that's, maybe makes it more something that I'm interested in. So if you didn't do it right on the homework, hopefully you can figure out what you did wrong. And then, I have to repeat myself often. I guess it's part of my job. I'm not out to try to get you to get a low grade. I'm trying to make sure that I can measure that you're retaining the things that or not retaining, but you're capable of doing the things that are the subject of the course, right? So if you can't do a planetary gear, after we did a homework with it, I want to know that something. I want to know, like, hey, can you do this problem right here, right? There's gear force problems, I think. Yeah, there's a gear force problem. Need to be able to do that. Here's one. I think this is also, yeah, this is like, bearing. I think these are the loads on the bearings. Yeah, you're supposed to find out. So, pretty straightforward problem because it's symmetrical. And then speed of gear compound. Yeah. This is a basic question you should be able to do. And okay, so here's chapter 14. Now this is a non-AGMA thing because it's near the beginning of the problem set, right? Same thing true here. Yeah. So anybody have a request for a problem type they'd like to go over?
Yeah, could you go back a couple slides to the sun one? So I did most of it correct, but I have like a small question.
Which one?
The sun.
You got a number?
Oh, you just passed it.
This one?
Yeah. So
Okay.
my question, or at least like where I went wrong, and I looked at the answer key, so I kind of already know the solution, but I was looking for some more clarity. When we're using the equation that has like the NL and NC and NA and all that stuff is equal to E. Well,
Yep.
when I was doing it, I applied the how do I explain it? Like the tooth ratio from 2 to 3 in order to get to the arm speed. Inside I think it's like NA, which is a driving or something like that. And then also have to be on the outside. And so I guess my question is the reason why that's not supposed to be there because it's already accounted for?
I think it might be better if I just go through the problem.
All right, that's cool.
because I don't quite understand like what you're asking, but that's totally cool. So let's see. I think I can do this right here at the same time as that. So, and hopefully we can get this guy to focus a little bit. Mm, okay. So, yeah, my method, I always have to draw the thing. It helps me. I don't like not to have a picture to base the thing on here. So one of the quirks, one of the weirdnesses of this problem is that you have to notice these dashed lines. This one's not so bad. Okay, arm kind of comes up like this right here. I kind of exaggerated that too much. And that's a dash line right there. Dash line. I think that's a pretty big one right here. He comes through here. And you can see this dashed line right through there. And then here's one that you have to notice that this thing has see those little things right there. That means that this guy can't move. I think I made him too big. Didn't make him symmetric. Here, I'll cut him off. Make him a little more symmetric. There you go. So, and so the tooth numbers are, this is number 2, 3, 4. They decided the arm was 5 for some reason, 6 and 7, right? And so N2 is equal to 20, N3 is equal to 16, N4 is equal to 30, N6 is equal to 36, N7 equal to 46, and gear 7 is fixed. If shaft A turns 10 revolutions, right? So they might as well be, you know, they say number of revolutions, but it might as well be revolutions per minute, right? So you just think of that as RPM. So 10 revolutions, whatever. So the process here is first to find an E based on the gear layout, and don't forget about who can move and who can't move. So we go the driving on the top. So we know that N2 drives N3. N3 drives N4. Then N6 drives N7. So did you get that? Like what that part of it?
Yeah, I do.
Okay, cool. So we don't even need to put 3 in there. You can think of that 3, its sole purpose is to just separate 2 from 4 the correct amount of distance, because it doesn't do anything. It does reverse direction. That's one thing. And here's also something we because of the nature of this, what we should do, we need to decide what the sign of this whole thing is going to be. I think because we don't have any internal teeth, we have all external teeth. We could, I think we're going to be okay with the negative, negative, negative makes a negative overall. But what you want to do is the other way to do is like you fix the arm, right? And then you see what happens in the rotation. So you can go like, I'm going to assume this is a counterclockwise, right? So that means that this one's going to go clockwise. That means that one's going to go counterclockwise. And that one's going to go counterclockwise because it's on the same shaft, which means this guy, if he could move, would go clockwise, which is the opposite of this right here, right? So because it's the opposite, yes, the whole thing will be negative. But you could also, I think you could probably reliably go through and go every stage reverses direction, and there's no internal teeth. The internal teeth is the thing that screws things up. because they don't reverse direction. So anyway, we'll get the right number here. Go 20, and I'll put 6 in there. 36, and 4 is 30, and then 7 is 46, right? And the whole thing has to be negative. So we end up getting 20, 36 times 30 divide 46 divide. So we're going to get a negative 0.5217 is our ratio. And now, let's see, I probably don't want to rely on my memory, so I'm going to go to look up in the book the equation that we use along with this for the for planetary gear. So come on, open it. I think Adobe has been giving me problems lately. He's just angry at me. I feel as though it's its fault. That's I'm gonna start blaming Adobe for everything. I'm used and abused it too much. That's what it is. Let's see. There's a planetary gear. Is there a planetary gear? I don't even know there's a planetary gear section. There's gear trains.
705. Or that's it. Oh, that's actually what I was talking about on the bottom of the screen. But I don't think anyone asked me.
Yeah, this is the equation that we need right here. You go NL minus NA over NF minus NA. Okay, and so what you have here is this is the arm, this is the last, and this is the first, right? And it's regardless of what is actually moving, right? So 2 would be the first, and 7 would be the last, and this would be the arm right here, right? So that's what the A is going to be. So what you want to do is this guy right here, he's going to be NF as far as this is concerned, and this is it. And so NA is the thing we're going to want to get. So what we say is we go 0, right, for the last one, minus NA is the thing we want out. NF is going to be 10. And let's just say that it's counterclockwise. I don't think they say in the problem. Turn 10 revolutions. How many turns will the shaft B make? But we'll see here, right? So we got NA right there, and that's going to be equal to a negative 0.5217. So now you just have to go through and do the math out of the thing, right? This is a first off, we get rid of this right here. We have 10 minus NA right in there. And so what that NA is going to come over here is going to have 2 NA. And then that's going to be 5.217, right? 10 times that. Oh, I did that wrong. Sorry. Dumb. Math. Pesky math. I need to do this in stages here. So 5.217 minus 0.5217 NA. Now I can go NA is going to be, all right, so that's going to be 1.5217, right? It's going to go over here. It's going to add to that thing.
Is
then we're gonna
NA
divide.
3 or 5?
Say again?
Is NA 3 or 5?
NA should be 5. Arm 5.
Okay.
It's the arm.
All right.
And let's see. I wonder if I did this right. Let's see. Divide. Yeah. So I get 3.429. How did I do? Yep, there you go. 3.428. Sure. Pretty close. Does that make sense?
Yeah, it makes sense. I don't know. Like I'm having like convince myself that this equation makes sense.
Yeah, I know. There's a little bit of faith in this one.
Yeah.
We could. There's other methods to approach planetary gears. I think they're more confusing than this.
Yeah,
Quite frankly.
it's simple. It's just I don't know, the logic is kind of lacking.
Yeah. I think for something along these lines, I think the approach of setting this up and then and then just proving to yourself that it works, right? Like by way of, I don't know, the little pass around things. I know that we didn't do that, but you're just gonna have to have a little bit of faith that this equation is relevant. You're gonna make an appearance.
No, I don't want to make an appearance after working out.
Okay, all right. She's right there, like the legend.
Woo!
The internet was hating me, so I had to.
Okay.
Hmm.
I'll get out of your hair.
She's shy.
I'm all sweaty.
Yeah. Nasty. Any requests besides having Mrs. Deal teach the rest of the class? You can ask me anything.
Oh, I just have a quick question about just that problem we were going over.
Okay.
So when it says gear 7 is fixed, does that mean like is our shaft B and the arm are they separate? And then gear 7 doesn't. I'm kind of confused on like what's moving and like what's not moving.
I hear you. I hear you. I don't know if I somewhere I have made a model of this. It's so much easier to see to see what's actually taking place when you can put together a SolidWorks model of any of these things, just to kind of get a better sense of what they look like. But with my connection issues, I would be but I would love to be able to like show that instead. It's probably not a good idea to attempt to connect to my computer in my office and look for those SolidWorks models. But so the
Oh no.
We lost him again.
Yep.
did I lose you?
Yeah, you cut out. but
Yeah,
I
you're
think
back now.
I cut out.
Yes.
Yeah, you're here now though.
I'm sorry. I put in a thing to Xfinity with a little complaint thing, and they asked me if I wanted to restart my modem. So I was like, that's just going to delay all of this even further. Yeah. So did I say anything? Did you hear anything where I did that maybe made it clearer
Right,
of what?
right when you were about to explain it, it just completely cut out. Like so.
Oh, okay. So, yeah, so the dash line, maybe that helps a bit. That's right here where shaft B is passing through 7. And then you see the little gray things that makes trying to indicate that 7 is fixed. So you kind of picture that thing's, just that everything is revolving around this 7, and this arm moves, and these interconnections between each of these gears end up driving this shaft, or it actually works the opposite way, right? So the A is actually causing this whole thing to rotate, and the output is B.
Okay, I see. So this dashed line between, like in the gear 7, indicates that it's free from the shaft, and that's staying.
Yes.
Okay,
Yeah.
I
It,
see.
it it's it you- it's really, it's kind of subtle until you see it, right? That it's there. But this is definitely a good candidate to make a SolidWorks model out of, so that you can see it. And I know I have before. I just don't know if how if it survived the great ransomware attack of 2020, because I lost a ton of stuff because I had it all on my local computer as opposed to having it on OneDrive, because I had some bad experiences trying to do SolidWorks over network drives. So I had the habit of almost all my other files are always on OneDrive, but for those I had them on my local machine, and then when I lost I lost everything. Fortunately, OneDrive was able to reboot, but I lost like over 20 days worth of stuff that was on OneDrive even. But I had all these SolidWorks files for all kinds of problems and stuff, and I don't have them anymore. But I got to remake them. This is actually probably a pretty good task for a homework, but you already have a lot of stuff to do for homework. But it's pretty. It does making any of these planetary gears in SolidWorks a real big benefit to getting to visualizing what these things actually look like. This is probably one of the dumbest problems right here. I kind of think this problem is stupid, because I don't know how you would ever drive 6. It's like impossible to drive 6. You see, 6 is driven by 12 RPM, but there's just no way that you would ever be able to do that. I don't know what method you'd be able to make so that 6 would be the driver in this thing. If you look at it, it's this thing be swinging around no matter how you tried to make 6 turn, or how you would connect to the thing. It just wouldn't work. I don't know. It's a stupid problem.
Well, yeah, because it's not connected to any shaft, right? So,
No.
huh.
And anything, if you try to put like a gear to the side of it, this whole assembly swings around, would rub it right into it. I think it's this arm that I'm going to blame. It's like this arm doesn't need to be here, right? So what you could do if that arm was missing, you could have a shaft within a shaft that was connected to 6 and making it move, or you wouldn't even need that. You could actually just have it connected over here. Yeah. So there's really no reason to have that extra arm that's like right onto there. But yeah, whatever. So want to pick another problem? Pick another problem type. I'm here to help. That's what I'm here for.
I see one of the AGMA problems for chapter 14. I think 14.20. If we could go through that one, possibly.
Okay, cool. That's not 1420. Where'd you go? There you go. Okay. So boom, boom, boom. Right. All right, so we got 20-degree pinions, got 20 teeth, and it's got a module of 2.5, so it is an SI problem. The power is 120 watts. The gear is 36 teeth. The pinion RPM is 100. And they're made out of, let's see, so a grade 1. It's got a face width of 18 millimeter and through hardened steel. And it's got a Brinell hardness number. Can't remember how they were. This Brinell hardness number of 200. Uncrowned, and they're telling us that it's got a number 6 quality. All right, so that's that QV thing. And considered to be open gearing quality installation. Yeah, that's for the KM thing. We're not doing that. So find the AGMA bending and contact stresses and the corresponding factors of safety for pinion life at, does it say 10 to the 8? I think 10 to the 8 cycles. Reliability of 0.95. Okay, so got a lot of stuff on an AGMA problem to have to go through. But we start off, probably the best thing to go with is to try to, write down our equations and then kind of like see where we want to get all that stuff. Let's see. It's probably somewhere near there. No. Boom. All right, so first things first, we want to get this main equation, WT KO KV KS PD over F and KM KB over J is our main equations here. We also are going to want to get later on, I'll write mine over to the side, my allowable STYN over SF, but we don't use the safety factor because we're about to try to find the safety factor, so it doesn't make any sense to put that in there. Yeah, so we're actually going to find safety factor this way. I use this. I wrote down the wrong equation. Let's write this: YN divided by KTKR divided by the stress right there. Okay. So let's just focus on that one first. So what we need to do, go down this list of things, and I probably want to find this WT first. So combining with this horsepower and this RPM. Now this is SI units, so most of the time I'd probably use this equation if it was US units, and I would find that V. But you see, we don't want to use this equation because that one has the 12 in there, is because they want feet per minute, right? So we haven't really done a metric one before. Let's see. Do we have this equation at the beginning? I think we might. The stuff that we need for this. Yeah. All right, so let me see. I think the best place to go get this is in chapter 13. I can just figure it out on my own, but well, I think it's better to try to get you the equations, or get you to the place where you want to get the equations. So here is what you would do. Yeah, right there. You have a WT. We're going to find, let me see, I'll write down, I can put this over to the side. I can get rid of him, get rid of him, put him over to the side right there. Okay. So find my WT is equal to 60,000 times my NW here, oh, H here is in kilowatts, right? So we don't actually, I guess if I wanted to make it easy enough, I go 0.12, right? So now it's in kilowatts, but I could have got rid of that part of the thing. Pi, oh, I need D. So that's actually usually a really good thing to do. First is find the diameter of the pinion. In this case, because it's metric, we take the module and multiply it by the, it's the module multiplied, see, come on, there you go. How come I can't make this thing tall enough to get all that in there? I'm really messing this thing up. There you go. We multiply the module by the number of teeth, right? So they told us the module was 2.5 and the number of pinion teeth were 20. So this is sad that I'm going to write that in my calculator, but I did. It's 50 millimeters. And while we're doing it, we might as well get the gear. So he's going to be 2.5 times 36. And I don't feel bad for using my calculator for that. So 90 millimeters. All right, so, and for this equation, they are using the diameter in millimeters. So we can go and say 50 millimeters, and then the RPM, it's gonna just has to make sure we're using the diameter and the RPM for the same one, right? And those are both for the pinion. So we get our 60 times my 120, and then our good friend pi, and 50 and 100. And I don't like that it's a small number. And see, I got, that's a fraction. Is that right? 60,000.12. That was dumb. But 50 divided 100 divided. Yeah, I guess that makes sense. All right. Pretty small number. 0.381 or 20. But these are kilotons, right? Yeah, that's the transmitted load. That's the units that this will give me out. And I got to see when I get back. I got to be careful. I like to switch back to base units for things. So when I get to this right here, I'll probably, unfortunately, this we might want to adapt to this, right? So we don't, this doesn't belong in the when we're doing the SI version of this. Let me it's gonna make this thing small. Come back up to the AGMA stress equations here. And yeah, you see, you can see that the module actually, and they actually call the face width B for some reason. That doesn't make any sense that they would all of a sudden. I guess they didn't like F, but anyways, that's the version that you would have. Well, they also stick a YJ at the bottom, but it's going to be the same, right? So they said this is B and M, and they call this guy YJ if you're going to be literal for this problem. And okay, they didn't say anything. So they didn't say, I got the WT, they didn't say anything that I think are clues to whether that you would use anything for the overload factor. Okay. Oh, wait, my WT is wrong. What did I do wrong? Son of a gun. How did I get it wrong with WT? What the hell? How come? What did I do wrong? That's right off the. That's great. Right from the very beginning, got something wrong. Right off the top. 120 watts. Huh. All right. Well, when in doubt, go to the stinking solution manual. Where you go? Machine design. This is a great session. I'm not sure this is the same problem numbering.
When I calculated it, I got 0.458 kilonewtons.
So you got it right, and I got it
Okay.
wrong. I don't know.
'Cause
Why?
put in
Why
the
did I?
same- I must in the same numbers that you have. I mean, it must have just been like a calculation
Yeah.
error.
Yeah, that's me. That's what I do. All right. Do it again. Sick. Yeah, no, I did get it. Okay. Yeah. 4, 5, 8, 4. Right. See, first time I got
Yep,
it right there. I
that's-
got.
yep.
I don't know what the hell's wrong with me. Okay. So yeah, and then looking at here at the numbers that KO, yeah, we could say KO is equal to 1. I guess we just have to assume it was 1. KV, this is one that we're going to have to look up. They gave us we might have to do a conversion for that one, I think, in order to use the book's figure here. This thing right here, because there's feet per minute, right? So unfortunately, they don't have the metric equivalent of feet per minute. So I guess I could try my best to do a conversion on the fly, right? But first I need a velocity, right? So I need to go back. I guess I could do this. Okay, so what I'll do is I could turn my diameter into, so he's 50 millimeters, and I know that there's 25.4 millimeters per inch, right? And then we would have, sure, all right, that just gets it. So it's going to be 2 inches, really, 50, 25.4. So, 1.969 inches. And V, we know, is pi dn over 12. So 1.969, and it was 100, and so divided by 12. It's actually a pretty small number, relatively speaking, to this feet per minute that we would use, right? So it's really it's tiny, 51.54 feet per minute. So coming back over to here, it's actually nearly impossible to use that curve here, right? Because this is 2000, so you're really looking at it. You can see quality is 6 right in there. You almost have to use these equations to be able to do that. Oh, look, they had a meters per second one there. Okay, so that solved a problem. But it wouldn't matter. We already got the thing out, right? But then I've urged you not on an exam, do not use these equations. They'll just take too much time. But in this case, we don't really have much of a choice. But so you have to go backwards here and start out with the B. What is this over here? What is on the next page? What was this one right here? Oh, that's the max. All right, that's why that's there. Okay. So 2, 5, 12 minus, we were told 6 is raised to the 2/3. So you're going to raise 6 to the 2/3, raise it up, boom, and multiply it by 0.25. So you end up with 0.8255. And I can't emphasize enough, do not do this on an exam. 50 plus 56. Just eyeball the thing, but this one would be impossible to eyeball. So put that back in my stack. Need to sauce another times 56 plus 50, boom, and I end up with 59.77. And now we're at the KV, it's a big K. We're gonna go 59.77 plus the square root of 51.54 divided by 59.77, all raised to the 0.8255. And so I have to go, I think I just got out of that, 51.54 square root, add it. And now I want to flip it and divide it. Oh, good. Hey, I kept it in the stack. Good. And now I can raise that to this. Boom. And 1.0982, right? So very small. So let's see if they agree. Yeah, right there, 1.099. KS, just assume that one, right? So the KS is a pain, I think. No, that's the size factor, right? Yeah, the size. I think that's a size factor that they go through all this stuff right here, but they basically say use 1 right there, right? All of that. And it makes you want to have a little My Little Pony looking, little raising his arm, like what the hell? I don't know. And so say KS is 1. And the next one, okay, so KM. Oh, wait, I put 2 KMs in there. I think I messed up. I gotta find out which was supposed to go in there.
I think it's
The
supposed
load-
to be KN. Is it not? I'm not sure.
Yeah, I forgot. I thought there's a KB somewhere. Let's go back and look. Kaboom. Yeah. KB. So KM, I'm never asking you to do this because it's a long, involved process here, right? To get KM, this load distribution, because you have to go through this equation, but then you have to find each of these things. Well, that was not too hard. That's just one. But here you have to go, this is the face width, right? So you have to, and we would have to convert to, right, to be able to do this. And then, I guess probably straddle mounted, sure. And then you have to find this ABC down from here, and go through that. And when everything was said and done, what we would find, KM is 1.270, right? So yay for going through all of that. 1.270. If I were to forget and not give you that for an AGMA thing, just come up to the front of the room and slap me. No, don't do that. That's not nice. No one should slap anyone. So anyway, I think we got all of the stuff. Well, no, we need the Y, this YJ right now. So we know that, by the way, this is the rim factor. And if you don't have a rim, then you don't have a factor, right? So you don't need to do anything about the rim factor. I don't even know where that is. Where they say right in there. Yeah, there it is. Okay, the rim thickness factor. We weren't told anything about the temperature, so we're going to leave that as equal to 1 when we get to it. We do have to get the shape stuff, though, out of the way. And I think he's up here. And these are interchangeable, this J and this YJ, but I just wanted to point out the equation in the books is to use YJ, so I figured we might as well just write it that way. But it's already been done for you, so they're equivalent to each other. And this one requires to be zoomed up quite a bit. All right, so there'll be 2 separate ones, but let's just look for the pinion only. But we have a 20 tooth pinion and a 36 tooth gear. So we want to find for 20, this is the number of teeth for which geometry is desired. This line right here, and there's a 35, right? So we can trace that down there, and let's see, I'm going to count up 1, 2, 3. All right, so it's the 3rd line from the bottom. 1, 2, 3. That to me looks like, let's see, 1, 2, 3. I would say 0.335 maybe. I'm guessing a little bit like what did I call this thing? I called this a YJ. 0.33. I don't know, a little bit more. You could argue about it. 1, 2, 3. It's a little bit more. I go 336. Let's see what we said before. They went 330. Okay, well, just be that way. And then I said 0.38 for this one. All right, so that would be this guy, like near this 35 and near the bottom. Okay, sure. Here's 36, 37, 38. Yeah, okay. I go 0.38, sure. I'll buy that. Can't I get him? Why can't he fit visible? Fit visible. I don't want to get rid of the rolling. I don't know why I did that. Okay, so I think I got everybody here for my stress. So I can say I'm going to go for my base units. I prefer base units when trying to do calculations, so I don't have to worry about conversions. So I'm going to use newtons and meters. So this is 458.4. Putting it in for this equation right here. 1 for my KO. My KV is 1. Where'd you go? 0.982. My KS is 1. And they put this 1 here. They put module on the bottom, but the module is in millimeters. We need to turn that into meters. So it's 0.0025. Yeah. And then for the diameter, no. Let's see. I'm saying that wrong. I have face width. All right. So face width, the face width is 18 millimeters. All right. So I need 0.018 right there. And I need my KM, which I decided to give us because we're not going to go through the rim factor is 1, and now we're going to divide by 0.330. According, I said it was 336, but I guess maybe I was pickier than they were, or I read it wrong. So plugging through all those, 458.4 and 1.0982, divide by 0.0025, divide by 0.018, multiply by 0.270, and divide by 0.33. And I'm left with 4.305 E7, right? When those are pascals, so I could see that that's obviously 43.05 megapascals. I usually just do this part and then don't bother writing this down. I just jump to right there. But that's just for me trying to keep the units straight for SI, because I hate it when I get this stuff messed up. So okay, I got the 43.08 megapascals for that. And now we want to go to the part of it where the main thing they're asking for were the safety factor, right? Let me see. Oh no, we want to find the stresses and the corresponding factors of safety. So I'm going to fill out this equation right here. So what I need is the material. This is actually, it's kind of weird. They keep calling things allowable stresses. So that's not even a strength. This is actually an allowable stress, bending fatigue stress. It's got a bunch of factors. Factors. There are other factors thrown in there, right? But it's essentially an adjusted endurance strength. And then this is a life factor right there for the fact that we're evaluating it at a different number of cycles than this one was set for. KT and KR, this is going to be the temperature one, and then this is going to be the reliability factor. So this was the easiest one to look up for right now, so we can get that KR. They said it was 0.95 reliability. So I think it's down here somewhere. And that's just a table, right? So we don't have to. Yeah, so 0.95. Oh, well, I think we have to interpolate, or I guess we could use this factor right here. So they decided to take a little equation for us. Okay, so we could do the equation. I don't mind. It's not that hard of an equation. So plugging him in for 0.95. What is that? Okay, so we have. I could do this in my head, but I'm not going to do it. I'm just going to do it with my calculator. So we got take the natural log. Where's our natural log button? Hit the blue thing. Hit that. Raise it up and multiply it by 0.0759. And that became a negative number, so that becomes positive. And we're adding that to 0.658. And so we get a factor of 0.8854. Let's double check and see what we got. The numbers 0.8854. Where's our KR? I don't see it. Where'd you go, KR? You're leaving me. You're letting me down, man. There he is, 0.885. Yeah, okay. So we're good there. And then we need the YN. Oh, we also need the ST. So that's okay. So let's do the ST first. All right. So we were told that this thing is grade 1 through hardened. I believe that's going to be this guy right here. Do we have? They didn't do us any. Oh no, here it is. Okay, they got over to the side. They had SI over on the side. Wait, this is the contact one. I'm reading the wrong one. Yeah. Okay. Yeah. Should have been careful there. More careful. So here you go. Here's grade 1. we have to do this over to the side. So the SI equations are, here you go. This is for grade 1 right there. So write out ST is 0.533 HB plus 88.3, and that's going to give us megapascals. So this was Brunel hardness number of 200. And if we put in 200.533 times our 200, and then we add in our 88.3, we end up get 194.9 megapascals. And we need this YN now. And I think he's down. No. There it is right there. So we need, let me zoom into this side. All right, so we are going to be to the right-hand side over here. And we're going 10 to the 8 is what we're going to put in for N. We have a little bit of a choice to make right here because you can't decide whether to use the upper one or the lower one. I think, you know, this is the choice of YN in this shaded area, which is what they mean by there, is influenced by all of these things. And I'm not sure which one they necessarily would have picked out. I'll pick the top one. You know, it's a matter of, I don't know. You could just make your preference. I don't know. You could argue it maybe with somebody. So what is that? 1e to the 8, right? That's what I would use for there. And then 0.0178. Raise it to it and then multiply 1.3558 times it. So we get 0.9768. What did they get? What was their in between number for that? Yeah, they got 977. So sure, that's the one that they probably picked. So I think we got all the stuff that we need for this equation right here. So we have the safety factor is going to be that, where did you go with this? Right there, 194.9. YN is 0.9768. Divide that by 1 for my KT, and my reliability is 0.8854. And then divide all of that by the stress. And this is megapascals, and this is going to be megapascals. So we're going to be okay with our 40, whoops, fell off the edge, 43.05. And I could still, I still know a stack. See, but what I'm saying is the calculator, you know, has the little stack thing, so I can just hit the divide symbol right here to divide. See, save me a nanosecond, and then divide that by 43.05 and 4.99 is my safety factor. That's a lot. Yeah, but there you go, 4.99, right? And don't give me an extra decimal place. That's enough for a safety factor, right? So
I just have a quick
all right.
question.
Okay.
So when you were choosing to decide, I think it was the table for YN. When it says it's influenced by the like all the things that it lists,
Yep.
does that mean like if it's higher, if those things are like higher or lower than you'd, so like if like pitch line velocity was higher and like residual stress was higher, like which one would that like lean towards? Like the lower one? Or?
I'll be honest. I don't know.
Okay.
So we have to kind of think about it a little bit.
Uh-huh. Because if
Yeah.
something was faster, would it, or would you want to go the more conservative approach? Or for-
Yeah, I think so. I think you know, if something it I think this is a tough one to really say for sure. Um, you know, and we're talking really small amount of changes, and except when you're up, maybe up to here, right? They starts to get smaller and smaller the amount of influence that you have here.
Uh-huh.
You can almost think of these, you know, for some of this might be for trending, you know, we can say, oh, this is a tendency. So if something is more ductile and more fracture tough, it's going to live longer, right? I think.
Okay.
So therefore, I would use the upper line. If something has residual stress in it, that could be a good thing and a bad thing. But I think but for the most part, I think in this context, it'd be a bad thing, right? And I say it could be a good thing, it's a bad thing, because if you have a compressive residual stress in something that's going to be flexing in tension, it's actually can be a good, right? Because it relieves that residual compressive stress. But if it has a tensile residual stress, they're additive, right? So it could get worse. So without knowing what they mean by the residual stress, you just think that it makes it worse, so it doesn't live as long. Cleanliness obviously would live longer if it was cleaner, I would guess. I mean, it just one's better than the other. And a higher pitch line velocity, sure. What you're saying, I think it would live, you know, less if it had a high velocity as opposed to low velocity. So that would be my guess. But it's interesting because we do have, I do believe, I don't know, you were able to find it quickly, right? Find the Iranian upload version of the electric boat AGMA.
Yeah,
thing.
I found it pretty fast. It wasn't too.
Yeah. So I think that there's probably this is like a direct thing that's like right in there, and I don't know if there'd be more explanation, but there might be some more explanation.
Okay. Cool.
I just want to point out my battery sticker. This always amuses me. It says like no babies, right? No baby, but no don't feed the baby batteries, and they made a sticker for that. And perhaps people didn't like the words weren't enough, so they had to make a symbol for this little baby. And they're saying I think the ages of this is 0 to 6. Above 6, let them eat all the batteries they want. They're not babies anymore. It just amuses me. So anyone got any requests for a problem type? Or you want me to talk more about this battery label right here? Because I will.
I think I'm all set. I'm probably gonna head out now.
All right, cool. Thanks.
So yep. Thank you.
Eli and Jacob number 2. Says so right there. It says Jacob number 2. If you run across Jacob number 1, watch out. He's aiming for it. He's coming for you.
I have some quick questions for the homework, but I don't know if
That's fine. That's cool.
one of them's for the gearbox. When we were finding the overall reliability, would it be the machine? So it would be all of the bearings that we would be using. So it wouldn't just be like in that one shaft. It would be, every single bearing.
Ooh, that's a good question. Now you're saying homework 6?
Yes.
Huh. I'm trying to think about that. How did I phrase that?
Well, it'd be related to our project. So you said in the whole machine, but would that have much effect if they're not really like on the same shaft or part of the same?
I think it's a really good question. I'm not sure. It goes to what my intent was, but it also comes into a sort of a philosophical thing, right? So, the total machine reliability due to the bearings is to be 92%. So I think, that you would have to take a serious freaking, yeah. So there's 1, 2, 3, 4. You'd have 8. Would you take it to the 8th root for 92? That would be freaking crazy.
And then mine has
Well,
10, I believe.
You have 10. That's insane.
So
It's
yeah,
insane.
I don't know.
Yeah.
I've been doing it
Yeah.
calculated with the 10, but it doesn't make too much of a difference at that point. So
Yeah, you need 99.16% reliability. That's a lot of reliability.
yeah.
But that's not terrible. I mean, 99% reliability. Okay, yeah, sure. That sounds fair. I don't know. Let me see. I'll look at my. Let's take a little peeky poo. Peeky poo? Did I actually say that out loud? I think I did. Yeah. Words. Let's see what happens. Let's see. I haven't looked at this solution in a while, since October. So I don't know. Well, this is a different problem. Oh, that's problem 2. Oh, I guess I didn't do problem 1. Oh, okay. No, I didn't do it yet. I didn't write up a solution to it.
All right. And then for
But I would think that's a reasonable thing to be 99.2% reliability. It isn't awful.
all right.
But if it means that the bearings have to be like twice the diameter of the gear, then yeah, then we know that we've made it too stringent, right? So that would be my caveat there. I was like, if I accidentally made something that can't be done, we need to, adjust.
All right. And then for problem 2, I think I did it right, but it has a lot of iterations. I've found myself like keep on going up and up and up in the sized millimeter bearing.
Huh. Because I don't think I had to do too much.
Because in mine, I had to do the prelim, and then I had to do 4 iterations after that to get one that would pass.
I don't think I've ever had to do more than 2 or 3 iterations most of the
And
time.
then one of them I got like really close, but maybe that's because my rounding was maybe a little bit different. I don't know.
Yeah. Yeah, this is being recorded too, so I'm just giving away the solution, aren't I? Yeah.
Yeah, well,
I think I did get iteration 3. Possibly could have foreseen this and just done it in 2. Yeah. I ended up getting like 80 millimeters. So I think it could be done.
you got
can have a
around
little,
80 millimeters for
I think
the one that you
I
ended
think
up choosing.
I think so. Yeah.
All right, well, that's what I got, so maybe I don't know.
All right.
All right, well, probably good enough. Then the third one, that one we had to use one of the things that you showed in the one of the videos that you didn't show in class of an example where you set the script L equal to I have it right here where it's L1 over uppercase L1, and then you set the that to F1 times just L, and then you solve for L. That's what I did.
I think so.
All right.
Yeah.
All right, so then that one should be good. And then for the first one, do you want a FBD of every shaft, of like all the shafts?
No, I
Said
think it's
that-
just the one I asked for, right?
Well, you said the first and the last, the output and the input, and then it said you must draw FBDs for each shaft. So do you mean by both of those? Because I've already driven like or drew all of them. So I mean, I already have. I've done all the calculations for all the 5 shafts of mine. So I mean,
All right, so where did I say? Let me read. For preliminary design, select a bearing for the input and output shafts based on the gears you presently have. You must draw FBDs of each shaft to find the bearing loads. Yeah, I just think I mean the input and the output. I don't think I mean every shaft, but you kind of have to, eventually you kind of have to do all the shafts. But,
I interpreted it as all of them. So you're gonna get all of them from me.
okay, cool. I'll draw smiley faces on them.
All right.
Um,
And then
in my acknowledgement.
a quick question on which way for the forces when you like do the when you're looking at a gear on a shaft, like is the input always like in the direction of the rotation? Like how do you decide like which way to put like F34T? If that makes sense.
Yeah, I'll see. I guess I have to do a for instance here. All
I always
right.
get confused by those.
I don't know why I just drew this way. Let me go here. All right, so let's say this guy is the input and he's going clockwise for some reason. He is 2, 3, 4, 5. So which one did you want to try to see here in this scenario?
Um, doesn't matter. I mean, if we could do the middle one where it's 4, 3.
Okay, 4, 4, and 3. Okay,
Because you have
so
two acting on it, and then it would be acting on 5.
yeah, so part of the thing we have to recognize is that some of the examples have had this gear and that gear just attached to each other, so you kept them together. But you shouldn't do that in this case because they are separated onto away from each other, right?
Yeah.
So you want to draw the torque instead onto the thing, right? So you said that you wanted maybe 4, gear 4 maybe.
Yeah.
Okay, so it almost makes it easier to like write them out kind of like over to the side. So this is 2, this is 3, and this is 4, right? So 2 is pushing on 3 that way right there, right? So what are we using? We're using Fs? Yeah, I think we're using Fs.
Yeah, we're using
this is
Fs.
2 onto 3 in the tangential direction, and this is 2 onto 3 in the radial direction. So if that's going that way, right? So there is some input torque that we're not seeing, but we call that shaft A right in there. So this is the torque A onto 2, right? It's putting it right here. And it's being opposed by this force right here, which we call 3 onto 2 in the tangential direction. And then we have the 3 onto 2 in the radial direction. Now, this shaft right here, we'll call this, okay, so this is shaft A in here, and this is shaft B, and it's in between. We've cut this shaft. So the shaft is actually putting on a resisting torque right here that we could go, this is torque B onto 3.
Mm-hmm.
But he's going to go, and by the way, I'm looking at this direction right here, so we have to remember that. We get to keep that up standard here. So onto this gear right here, it's going to have the opposite torque on there. And I'm leaving out the reactions right here,
Yeah.
by the way. Okay. Just making that, I'm not showing them on here. And I made my thing too small to be able to see. But here's, this is B3. This torque acting onto here. So this has got, this is no, not 3, this is B4, right? B4. Because this is gear 4. And so it's below it right here. So it must be coming this way right here. F 5 4 tangent must be coming in that direction, because this this thing is trying to turn it this way. So this is the 5 resisting getting turned.
So the torque will always be equal and opposite. They'll always be opposite from each other when they're on the same shaft.
Well,
when you
yes.
like that.
Yeah, you could think of it like as we're progressing down the line right here, that this torque is turning this gear, right? So it's the driving thing, right? And then, but then in this one, this force is the driving thing, and this torque is just a resistance to that driving force.
So it
But
doesn't really
now-
matter necessarily which way the shaft is turning to, it's like the direction. It's more based on the opposite of the torque. All right.
Kinda. I mean, you can also, alternative. Just remember that like power is torque times RPM, right?
Yes.
With a factor 63025 when it comes to
Or
US units.
33,000. Yeah.
Yeah, whatever. And so here, drawing over to the side is not a force, but here is the RPM of 2, right? He's going in that direction. And therefore, here's the RPM of 3.
And that would have the same direction as the RPM of 4.
Yes. Now, what you could think of is that the torque and the RPM are in the same direction because the torque is acting as the input power. So they agree with each other. But in this case, the torque is the output of this, right? So this is the guy that's the input, that 423. So he's actually agreeing with the RPM. Because you can think of that power has come from 2 and is going into 3 right here by way of this, but then it's coming out of 3 by way of the torque, which is because it's coming, you can kind of think it's flowing that way right here, and it's flowing into 4, right? So now the RPM and this torque, they agree because that's power coming into this, but it's being opposed by this because that's power output, right? So you can just kind of think in and out. It kind of come up with a narrative a little bit like that. So yeah, there is a connection to the RPM.
All right, because I've been struggling to figure out which way, and then once I do the sum of the moment, it kind of figures itself out.
Yeah,
Right.
It does.
And then for mine, on like homework 3 or something, when we decided to choose what gears we wanted, you said something about my gear with teeth 14 is usually too small. Is that something that you would want me to change like now, to go up to a bigger gear size, like above 17? Or like,
it's right there on the margin. I think it's fine. You can probably get away with it because you could do stuff to the teeth to like avoid that interference, to make it like just a little less of a chance. And if you're on the margins, maybe you could do some, it's not terribly important. But if you were to pick, there's a couple people that pick like gears that with really few teeth. So that I would insist, like if you'd only pick 10 teeth, I was like, you really can't do that. Yeah, but you're just right there on the border.
I think that's all I gotta ask for now.
Okay.
And then you just want an Excel spreadsheet PDF for the shafts as well.
Let me see. What did I say?
You asked for that. You said submit a PDF spreadsheet separately from the scan. Please perform these hand calculations, additional setup, a spreadsheet, so if the design changes, you can easily adapt.
Yeah.
All right. Okay. Does that have to be like too complicated or?
No,
All right. Mine's pretty
no,
simple
I'm
right
not
now.
gonna. I'm not gonna. It's mostly for you, right?
All right. Sounds good. And I think I'm all set here.
Okay, cool.
All right.
Well, I hope some people got something out of this. It's not. This was It started as a total cluster. Something else.
Honestly, I was just listening to it in the background while I worked on your homework, so.